Hello and welcome. We're glad you joined us. I'm Ilan Niska. I'm a Microsoft technical trainer. This course covers 6 sessions where learners will build a foundational understanding of core data concepts and how data is stored, processed, analyzed, and visualized in Microsoft Azure. In this session, we'll cover an introduction to Microsoft Azure data, non-relational databases in Azure. So let's get started with this session. Welcome to session 3. This shifts our focus to non-relational data in Azure. As we move through it, we'll build a clear understanding of what it means and why it matters in modern data scenarios. This session is organized around 2 themes. First, we'll look at the foundational ideas behind Azure Storage. Then, we turn on to the basics of Azure Cosmos DB. In this module, we will describe the features and capabilities of Azure Blob Storage, Azure Data Lake Storage Gen 2, Azure File Storage, and Azure Table Storage. Next, we will provision and use Azure Storage Count at a high level. Then we'll describe the key features and capabilities of Azure Cosmos DB. We will also identify the APIs supported by Azure Cosmos DB. And finally, we'll provision and use an Azure Cosmos DB instance, focusing on recognition rather than deep configuration. Let's start. This section shifts our focus to the core building blocks of Azure Storage. This is where we explore the different ways Azure can hold unstructured and semi-structured data and why these options matter for non-relational workloads. Azure Blob Storage is all about storing massive amounts of unstructured data in the cloud. A blob, short for binary large object, is any kind of binary data. That can be an image, a video file, a document, a log entry, almost any other file type that doesn't naturally fit in rows and columns. Azure Blob Storage supports 3 different blob types, each designed for a specific kind of workload. Blob blobs are the most common type. They're used to store large binary objects that don't change very often. Each blob is made up of blocks, and each block can be up to 100 megabytes in size. A single block can contain up to 50,000 blocks, which gives us a total of over 4.7 terabytes. Block blobs are ideal for things like documents, images, videos, and backups. Page blobs take a different approach. Instead of variable-sized blocks, page blobs are organized in fixed 512 byte pages. This design makes them well suited for random read-writes, where small portions of data needs to be updated independently. Because of this behavior, Azure uses page blobs to store VHDs, virtual machine disks. Append blobs are designed for scenarios where data is added only to the end of a file. Each block in a append blob can be up to 4 megabytes, and the blob itself can grow to just over 195 gigabytes. Append blobs work especially well for log and telemetry scenarios, where new information arrives steadily over time and existing data doesn't need to be changed. To manage that, we have what is called access tiers. Azure Blob Storage also provides access tiers, which help balance performance and storage cost. An access tier reflects how often data is expected to be used and how quickly it needs to be available. In higher tiers, data is accessed more frequently, so it costs more to store, but it's cheaper to retrieve. As data is accessed less often, storage cost goes down, but the cost to retrieve the data increases. This allows organizations to plan tiers based on how the blobs are needed over time. The hot tier is designed for data that is accessed frequently. This tier is typically used for active data, such as files or objects that applications read and write on a regular basis. The cool tier lowers the cost of storage and is appropriate for data that is still online but accessed rarely. A common pattern is to move data from hot to cool after it hasn't been modified for a period of time. Then you have an offline tier. The archive tier offers the lowest storage cost with a trade-off of longer retrieval times, sometimes hours. If you need to read an archive blob, you must first move it back to the hot or cool tier. This process is called rehydration, and it can take hours before the data becomes available. Because of this trade-off, the archive tier is best suited for long-term data preservation, where cost efficiency is more important than immediate access. To help manage data over time, Azure Blob Storage includes lifecycle management policies. These policies let you automatically move blobs between tiers as their usage changes. For example, a blob might start in the hot tier, move to the cool tier after it hasn't been modified for a while, and eventually be moved to archive tier. Lifecycle policies can also be used to delete blobs that are no longer needed. By automating those rules, organizations can store data more efficiently without manually managing every file. Inside an Azure Storage account, blobs live inside a container. Container gives you a clean and simple way to group related data together. For example, you might have one container for application logs, another for images, and another for backups. Even though you can arrange blobs in what it looks like a folder-like structure, there's no nesting of containers. Blob storage uses a flat namespace. That flat structure is one of the reasons blob storage scales so well. It makes the platform easier to manage at very large sizes without the complexity of a traditional file system. You also control who can read or write blobs at the container level, which keeps permissions simple and predictable. Even though blobs can be organized using virtual directories, these folders are not real directories. They are part of a blob's name, and the blob storage does not support folder-level operations. This is because blob storage uses a flat namespace rather than a traditional file system. Azure Data Lake Storage Gen 2 brings together everything needed to store analytical data at scale. It's built directly on top of Azure Storage, which means it uses the same highly scalable foundation as Azure Blob Storage. What makes Generation 2 different is that it adds a hierarchical file system on top of that platform. With this hierarchical structure, you can organize data into directories and files in a way that feels natural for analytics and bring big data processing. This makes it easier to work with large datasets while still benefiting from Azure Storage features like scalability and cost-effective storage tiers. Because Data Lake Storage Gen 2 sits inside of Azure Storage, it works smoothly with distributed analytics engines. Tools like Azure Databricks can mount the file system and process very large datasets as a single storage were part of the compute environment. This tight integration helps analytical jobs run efficiently and gives teams a consistent place to store raw, prepared, and curated data. When you create a Gen 2 enabled storage account, you enable the hierarchical namespace. This setting activates the directory-based layout that analytics systems expect. You can enable it when creating the storage account or by upgrading an existing one. It is important to note that this change is permanent. Once a storage account uses hierarchical namespace, it can't be switched back to flat structure used by standard blob storage. Data Lake Storage Gen 2 plays a central role in non-relational analytics on Azure by providing a single, scalable foundation for organizing and processing massive volumes of file-based data. Azure Files is a platform as a service file sharing solution in Microsoft Azure that provides cloud-hosted file shares using familiar protocols. It allows organizations to store and manage shared files in Azure while working with them the same way they would on traditional on-premise file server. File shares are hosted within Azure Storage account and can be accessed from anywhere with an internet connection. This makes it easy for teams to share and update documents across locations without managing physical servers or storage hardware. Azure Files integrates smoothly into existing workflows and includes built-in features such as replication for redundancy and encryption for security. The result is a familiar, centralized file sharing experience delivered as a fully managed cloud service. These file shares support the two major protocols most organizations depend on. Server Message Block, or SMB, is the protocol that Windows, Linux, and macOS clients use every day to browse, share folders, open documents, and work with network files. Network File System, or NFS, is widely used in Linux and macOS environments and works seamlessly in Azure Files if the storage account uses the premium tier. That is the only caveat. The premium tier is a requirement because NFS workloads often need more throughput and more predictable performance, especially when many users or applications are interacting with the share at the same time. In Azure Files, the platform keeps file data replicated so that if something goes wrong with one copy, we have 3 of them, and another copy is already in place to take over. Protections are built in, so teams don't have to think about additional backup hardware, server failover, or storage encryption. They just configure and use the file share. Azure Files fits into the larger story of non-relational storage options by covering the use case where you need share access to regular files, not blobs, not tables, and not documents inside of a database. Azure Table Storage is a non-relational way to store large amounts of semi-structured data. Each item is stored as a row, and every row has 2 values that make it unique, a partition key and a row key. Those 2 values work together to identify the item, and everything else in the row is simply a property. Rows can have different sets of properties, and that flexibility is intentional. It removes the need for a rigid schema and allows applications to store data that doesn't always look the same from one record to the next. Because this isn't a relational system, there are no relationships, foreign keys, or secondary indexes built into the service. Most solutions that use table storage keep the data denormalized. A single row holds all the information the application needs for that entity. That might be a customer with multiple phone numbers, several addresses, or records that have optional fields. Every row can adapt to what the scenario requires without forcing a fixed structure. The way Azure organizes data inside table storage is centered on partitions. A partition is a group of rows that all share the same partition key. Partitions make the service scale. Each partition can grow or shrink independently, and the platform distributes them automatically so workloads stay responsive. When a query includes the partition key, the service limits the search to that partition. It reduces the amount of data it needs to scan and helps the system return results quickly. Inside each partition, rows are stored in order by their row key. This makes 2-access patterns efficient. A point query identifies a single row by providing both the partition key and the row key. A range query returns a sequence of rows that appear next to each other in row key order. These patterns work well when the application chooses keys that reflect how the data is used, such as grouping related items together or retrieving order sequences. This design gives applications a fast, scalable way to store large collections of semi-structured records without the overhead of relational modeling. It's built for scenarios where the shape of the data varies, the access paths are predictable, and the workload benefits from distributing data across partitions. Now it is time for a demo. Let's explore Azure Storage for non-relational data. This demo will give you a chance to see Azure Storage. Up to this point, we've been looking at these services conceptually. Our blobs, files, tables, and data lakes fit into Azure's non-relational ecosystem. This demo is your opportunity to see those ideas in action. We'll provision storage, explore how the account is organized, and work through a guided exercise that walks you through the environment at your own pace. Let's open the portal first. Remember portal.azure.com. It is authenticating. Perfect. Now we need to search for storage accounts. Then create a new. There it is. Create. We need to give any resource. We need to give it a name. The name needs to be unique in Azure. Every resource needs to be using a subscription and a resource group. Remember, the name for the storage account needs to be unique. So that's a unique name. I'm selecting a region that is closer to me. Perfect. Washington State, West US 2. We'll select standard, which is good for demo for most use cases, and locally redundant, 3 copies in the same facility. That is what locally redundant means. We can also make it geo-redundant. That will be a copy to an additional region. So we can select that later. In this case, locally is fine. Good thing is that you just select the option. You don't need to do anything else. And in advanced, you see hierarchical namespace is one option. I don't click this box yet. I want you to see what happens if I'm leaving that with the defaults. So let's go next. You see this storage count is available for public access by default, opposite to the database. This is open to public. I'll leave that as is for now. Let's go next. For data protection, we have soft delete enabled by default in blobs for 7 days. But I'm disabling everything here just to keep it simple for our lab. Encryption is enabled by default. You cannot change that, so you don't need to worry about that. We'll leave that open. Perfect. Review and create. This is very fine. It will take a minute to create. After I click create, you can see on the top right, it is deployed. And also you have the breakdown of the deployment on the screen now. Let's wait. At the same time, we can download the file that I'm about to upload to the storage account. That's the file, a JSON file. Let's download this. Download this folder. Let's go back to the storage account. We can go to the resource now. On the left-hand side, you have data storage, where we can interact with containers, file shares, queues, tables. Let's open containers for now. And we will add a container. Let's give it a name. Look at the private option there. It is private by default. You don't want it to be public, right? So you will need to modify the options for changing that, but by default, it is private. Let's name that blob data. Now we can open the container blob. You see it is empty for now. Remember, this is a flat structure. So we'll talk about that in a second. We can obviously add a directory, but this is a virtual directory. It's not really a directory. And we'll see how it works. We can call it products. And you can see it seems to be there, but it is not really an object. We don't have any options. It is actually tied to the blob blobs. Let me show you. So let's upload a file. First, select downloads. That is the file that I downloaded first, upload. But I go to advanced. Now we'll upload the file not to the root, but I'll upload that to a folder. Let's call it product data. See, we have nothing there yet. Hit OK. And now the virtual folder was created at the same time. I'm clicking on the product data. You see, product data. And within product data, I have a file, like if I have a structure. But it's actually part of the name of the product.json. You see, I can manage the object directly here. I cannot manage the folder. See, nothing happens if I'm clicking on the ellipsis button. Let's download a different file. That's a different file. Save. And let's go back to storage. Let's upload the file. First, let's do an upgrade. And for upgrading, you need to review and agree to the changes. So we will do an upgrade on generation 2. You see, we have 1, 2, 3 steps. We started the first one, we accepted the changes. We will trigger the validation. That will take some time as well. And then we need to start the upgrade. That will also take some additional time. You can upgrade within this menu, or you can do that while you are creating the storage account at any time. Know that this is permanent. When you make the change, you will rename. Note that even though I upgraded the storage account, data is preserved. So that's our virtual folder, which was a virtual folder. And inside we have our blob. It's still there. Okay. It is a virtual folder. But what happens if I'm uploading the file that I had prior? Let's do that real quick. Let's upload. Browse. And here we have the product 2. Upload. We'll upload that to the root. You see, we have both files, product 1 and product 2. We can manage product 2, you see, as we could with product 1. Let's look at data folder now. And our product data folder, now, since it was migrated to a new structure, now we can also manage product data. It is a real folder now. Even though we upgraded that, we didn't create that again. It is now manageable. You see the access control list to the product data. Let's continue our demo now with the file share option. You see we have data storage for containers, file shares, queues, and tables. Let's add a file share. Let's name the file share Files. We could enable the backup. In this case, for the demo, I don't need to, but remember, this is a possibility, just a checkbox, and you have the backup enabled. I won't do that for the demo, but it is possible. Create to make it easier, and you see we have the SMB protocol already enabled to access the file share. If you click on Connect from the file share, you can connect from Windows, Linux, or Mac OS. You can download the script and connect directly on either of the systems. It will be readily accessible. Let's explore now Azure Tables. We'll select Add a Table. We'll call it Products. That's our table. And we'll interact with Products table from the storage browser. And we need to select the table. Here we can interact with any other services. In this case, interacting with tables. Add an entity. And remember, we needed to specify the partition key and the row key to properly identify any entity in the table. Everything else would be a property. Let's configure our first property. That's the partition key and the row key, remember? And we will add a property to our entity. First property will be name. String is fine. Let's give it a name. Widget. We can add additional property, the price. And it is a double digit. Let's make it $2.99. Perfect. Add. Now we have one entity added to our table. Let's add another one. You see, it is now another entity, so we'll give it a row key of 2 in the same partition key. We'll give it a name, still string. And a price, let's make it $1.99. We'll add additional properties. Let's say discontinue. And it will be Boolean. This case is true. Now you can see the schema on right. We have a different attribute for this entity that is not matching the previous one. And we did it without changing the schema. So let's pause for a second. We'll do a quick knowledge check to reinforce the ideas that we just covered. So first, what are the elements of an Azure Table Storage key? The first question asks about elements to make up a key in Azure Table Storage. Earlier, we saw that every row in a table must have a unique combination of a partition key and a row key. These two values work together to identify the item, determine how it is grouped, and decide where it is stored physically. That's why partition key and row key is the correct choice. Everything else in the row is just a property. Let's look at the next one. The second question asks about what do you need to do with an existing Microsoft Fabric tenant to support a data lake. The important idea is that Microsoft Fabric already includes OneLake as its underlying storage layer. Nothing extra must be added or configured to enable data lake support. Because of that, the correct answer is no action is required. The final question focuses on an organization might use Azure Files storage. Azure Files gives you a cloud-based file share that users across multiple locations can access. It behaves like a traditional network share, but without the hardware or the maintenance overhead. So the correct answer here is to enable users at different sites to share files. The other options describe scenarios better suited for data lakes or blob storage, not file shares. These knowledge checks are simply here to confirm recognition of the weak ideas. If you understand why each answer fits the question, you're in great shape for the rest of the session. This section shifts our attention to different part of Azure non-relational landscape. We've covered the storage services themselves, and now we turn to another way Azure handles large, flexible datasets. Question is, what is Azure Cosmos DB? Azure Cosmos DB is a multi-model, global-scale, NoSQL database designed for applications that need fast, reliable access to data across regions. It is multi-model because it supports several different ways to represent and work with data, not just one fixed schema. You can store information as JSON documents, as key value pairs, in graph structures, or in column family layouts. And the same service manages all of these forms. This flexibility helps when the structure imposed by a traditional relational model is too rigid or expensive to tune for every scenario. In a relational database, data is stored in tables with fixed rows and columns, and relationships are enforced through keys. That works well in many systems, but sometimes the shape of the data or the access patterns do not fit neatly into that structure. You might end up spending a lot of time adding indexes, refactoring schemas, and tuning queries just to keep performance acceptable. NoSQL models exist to give you alternatives to those cases. Instead of forcing everything into relational tables, you can use documents when items vary in shape, graphs when connections matter most, key value stores for simple lookups, column family stores for wide semi-structured records. Azure Cosmos DB brings all of these patterns together under one managed service. A key feature of Cosmos DB is its support for multiple application programming interfaces, or API. This API allows developers to work with data using the programming style and query language they already know from other systems, while Cosmos DB handles the underlying storage. Internally, the service uses a document-based engine, but the detail is abstracted away. The important point is that developers can interact with Cosmos DB as if they are using their familiar data store, and the platform translates those operations into its internal format. This reduces friction when teams adopt Cosmos DB because they don't have to abandon existing skills or patterns. To deliver consistent performance at large scale, Cosmos DB uses automatic indexing and partitioning. Indexing ensures that reads remain fast without requiring manual index management for every query. Partitioning splits data into logical segments so that the system can distribute storage and workload across many resources. As data volumes grow, these partitions help maintain low latency for both read and writes. From an application perspective, this means you can keep adding data and serving traffic without redesigning everything each time you grow. Another important capability is global distribution with multi-region writes with the turn of a key. You can have multiple Azure regions through a Cosmos DB account and enable write operations in those regions. Each region maintains a local replica of the data that can accept changes. This allows users in different parts of the world to work with the data in the nearest region. This reduces latency and helps keep the experience responsive. Cosmos DB manages the replication behind the scenes, so data remains synchronized according to the consistency settings you choose. Altogether, Azure Cosmos DB is designed for modern cloud-native applications that need flexibility in how data is modeled, predictable high performance, and the ability to serve users globally. It extends the non-relational story in Azure by providing database features like rich APIs, indexing, partitioning, and global replicas, while abstracting many of the operational details. This gives development teams a way to focus on building features and experiences instead of managing low-level database mechanics. Cosmos DB abstracts the complexity that typically comes with managing globally distributed databases. Instead of handling sharding, indexing, or synchronization manually, the platform manages those aspects automatically. Indexes are created and maintained for you without extra tuning. Partitioning is built in, allowing the service to scale efficiently as datasets grow. Cosmos DB supports application development patterns that rely on dynamic structures, event-driven ingestion, and distributed access. With this ability to run at any scale, from small prototypes to high-traffic global applications, it has become a core component in many cloud-native solutions. Let's look at API support in Azure Cosmos DB. First, Azure Cosmos DB for NoSQL. This is the native API in Cosmos DB. It manages data in JSON document formats, and it uses SQL syntax to work with the data. Then we have Azure Cosmos DB for MongoDB. MongoDB is a popular open source database in which data is stored in binary JSON, BSON formats. This Azure Cosmos DB MongoDB API enables developers to use MongoDB client libraries to work with data in Azure Cosmos DB. Then we have Azure Cosmos DB for PostgreSQL. Azure Cosmos DB for PostgreSQL is a native PostgreSQL globally distributed relational database that automatically shards data to help you build highly scalable applications. Then we have Azure Cosmos DB for Table. The Table API is used to work with data in key value tables, similar to Azure Table Storage. The Azure Cosmos DB Table API offers greater scalability and performance than Azure Table Storage. Azure Cosmos DB for Apache Cassandra. The Cassandra API is compatible with Apache Cassandra, which is a popular open source database that uses column family storage structure. Column families are tables similar to those in a relational database, with the exception that it is not mandatory for every row to have the same columns. Azure Cosmos DB for Apache Gremlin. The Gremlin API is used with data in a graph structure in which entities are defined as vertices in a connected graph. Nodes are connected by edges that represent relationships. Here we have two kinds of vertex, employee and department, and the edges that connect them. Employee then reports to employee soup, and both employees work in the hardware department. Now it is time for a demo. Let's explore Azure Cosmos DB. We've seen how Cosmos DB structures data and supports different APIs. This demo will give you a chance to see the service directly. The goal is not to configure advanced options or build a full application. It is simply to show you how it works for you to become comfortable navigating the environment and working with the core elements that users learn about. All right, we'll need to open the portal. There it is, portal azure.com. Let's search for Cosmos DB. Hit create. Remember, the Cosmos DB is the top level account for Cosmos DB resources. So we'll select the Cosmos DB for NoSQL. Let's select the workload type as learning. But you see, we can select different environments, development. We're using learning for the demo here, and subscription, resource group. And we need to give the account a name. Let's use this one. So that's available. Check, green, check box, perfect. Availability zones. For now, we are disabling that, but it is deploying to multiple data centers within the region. You can just with the tick box deploy that to multiple for availability. Let's select the region that is closer to us. In my case, Washington State, West US 2. And we are selecting provision throughput, which is by request units. You can also go serverless, where you're not paying if you're not using it. But remember that you have the request units. And we won't limit this one. Let's uncheck that. Let's hit preview and create. Validated, now deploying. Now that is deployed, let's go to the resource. You see, it was deployed to West US 2 as we wanted. We can have multiple read and write locations. We only allowed one for now. It is online as well. On the status, you can see we don't have any replicas yet. Let's go to the left-hand side and select Data Explorer. We will launch a quick start. This will allow us to work with a data set that is predefined by us, sample database. So we'll pretend we have an environment running already. Let's use the sample container that works for us. Hit OK. Perfect. So you can see the sample DB created. And we'll select items from here. You can see all the items that were populated to our sample database. You see bikes and some other items on the database. Mountain handlebars. Yeah, more items. So let's create a new item. So this is our template. Let's remove that, not ours. Note that I clicked save and metadata was added. This is to properly identify the items. So let's run a new SQL query. We are selecting every item. Select for C. Let's run it. There it is, all of our items. It will show 100 at a time. See, that's the full list. So we can see each item here in JSON format. We'll modify the query a bit. We'll filter the view here. We'll do a query that is partial. We'll select some. Instead of listing the whole contents, we'll search for the ones containing helmets. Okay. Only four on the list contain helmets. Perfect. There you have it. A simple query using SQL query. Let's pause for a second with this knowledge check. First question. Which Azure Cosmos DB API should you use to store and query JSON documents? Take a moment to think about it. The correct answer is Azure Cosmos DB for NoSQL. This API is designed to work directly with JSON documents and provides a SQL-like query language. It is the native and most common way to store and query document data in Azure Cosmos DB, especially when the data shape can change over time. Let's go to the next question. Which Azure Cosmos DB API should you use when your data is represented as a graph, with entities connected by relationships? The correct answer is Azure Cosmos DB for Apache Gremlin. The Gremlin API is built specifically for graph data. It represents entities as vertices and relationships as edges, which makes it a good fit when connections between items are as important as the items themselves. Final question. How can you enable globally distributed users to work with their own local replica of a Cosmos DB database? The correct answer is to enable multi-region rights and add the regions where you have users. This allows Cosmos DB to maintain replicas in multiple Azure regions. Users interact with the nearest region, which reduces latency, while Cosmos DB handles replication and consistency behind the scenes. These questions reinforce the core ideas you needed for choosing the right Cosmos DB API based on your data model and recognizing global distribution as a key capability of the service. In session 3, we explored non-relational data in Azure. We looked at Azure Storage services such as Blob Storage, Data Lake Storage Gen 2, File Storage, and Table Storage, and then introduced Azure Cosmos DB to understand how Azure supports scalable, flexible, NoSQL data scenarios. This concludes our session. We hope you'll join us as we journey through the course. We encourage you to watch other videos in this course or search out your next favorite topic on Microsoft Learn at aka.ms/learn.